Okay, in this video I'm going to begin my lecture on Chapter 15, which is entitled Impulse and Momentum of Particles. And so this will be approximately one typical day's worth of lecture with just a little bit of theory and several example problems. I hope you would have had a chance to look at this by class time on Thursday. And the plan would then be for us to work a lot more examples in class on Thursday. And there is a homework on this Chapter 15 stuff, on the first part of Chapter 15. And that'll be the material that will be covered on our next test happening next week. Alright, so Chapter 15. Impulse and momentum of particles. Particles we've already talked about. We'll turn to rigid bodies in the very next chapter, Chapter 16. Okay, impulse and momentum, we need to find both impulse and momentum. So what we're going to do is we're going to start off with an interesting looking version of sum of forces equal mass times acceleration, because mass times acceleration is mass times dv dt, but we could maybe presume that mass might vary with time. And if that's the case, then we really have to take the derivative of the mass times velocity property, which is mv here, and this quantity mv we call momentum. So the Newton's second law really says the sum of forces acting on the body is equal to the time rate of change of momentum of the body. And what we will do is move the dt to the other side, and we will integrate both sides. And so on the left hand side we're integrating force vectors dt from a starting time to a final time with a summation, because we might have multiples. And on the right hand side we would be integrating dmv, differential mv, from mv1 to mv2. Well, the integral of dmv is mv, evaluated it between mv1 and mv2, and so this just becomes mv2 minus mv1 right here, mv2 minus mv1, assuming that mass is constant, which we will for all of the chapter that we'll be working. So what we have from the left hand side integral over time is an integral of forces over time. This would be the area under the force time curve, and this would be a change in mv of the system. We will define this integral, which is the area under the force time curve, as an impulse. So the impulse is the integral of force dt over the time range. And so taking the impulse integral, equating it to the change in momentum, and for convenience we will generally write the equation that will move this starting momentum to the other side with a positive sign, and we will typically write it as mv1 plus any impulses, linear impulses, because we're talking about force vectors, straight line things, as opposed to torques. So starting momentum plus any impulses is equal to final momentum. That will be our key equation for the first 2/3 of Chapter 15. If we happen to have a system of particles, then we can put a summation in front of the mv's. So the sum of all the individual momentums plus the sum of all forces integrated over time to give us impulses is equal to the sum of all the final momentums of any set of particles. That's our working equation. I didn't print out an equation sheet, but I'll show that tomorrow in class, and we'll have a very small section on the equation sheet beginning the second page. I'll show that in class tomorrow. So let's take a look at some problems. Okay, and there's hardly anything more nice and practical in problem than a space kind of problem. So let me zoom in a bit on the picture and the graph, and then we'll look at the words. What we have is a lunar landing module from the Apollo space program, and the lunar module is plummeting toward the moon initially at 6 meters per second, and then it fires what to me sounds like a fairly short duration retro rocket to stop its fall. and this retro rocket has 2 seconds of ramp up in thrust, followed by 2 seconds of constant thrust. So it's only going to be on for 4 seconds, and that's a fairly impractical set of numbers. It was on for much longer than that, maybe even minutes. Okay, but we're going to go with it. The question will be, how fast is the lunar module falling, presuming it hadn't hit the ground yet, when we have allowed 5 seconds to go by. What that means is we'll have 2 seconds of ramp up, 2 seconds of engine burn constant, and then we'll wait a second and check our speed. That's what the problem statement says. Let's zoom in a little bit on the problem statement. If I can go any further, that's as far as I can zoom right now. So it says our 200 kilogram lunar lander descends into the moon's surface with a velocity of 6 meters per second when the retro engine is fired. If the engine produces a thrust for 4 seconds, which varies with time as shown, and then shuts off, calculate the velocity of the lander when t equals 5 seconds. Assume that it's not yet landed or hit the ground. Gravitational acceleration at the moon's surface is a pretty weak value of 1.62 meters per second squared. And so our solution to this problem, let me zoom out a bit so that I don't forget to move it around. Our solution to this problem is going to use our standard equation for the chapter, and we only have one particle to deal with. So the mass of the lander times its starting velocity plus any impulse vectors that occur is equal to the final mass times the final velocity of the lander. And to get things right in Chapter 15, we definitely need to draw free body diagrams. We didn't need to do that so much in Chapter 14 unless we wanted things like normal forces, but in Chapter 15 we almost always need to draw free body diagrams. This block represents the mass of the lander. We have mg acting downward, but a smaller value of g, and for at least for a time we have rocket thrust acting upward. And because the lunar is heading downward, we will choose y pointing downward as our positive coordinate direction. It is our choice. And so, fleshing out our equation, our mass is 200 at the beginning, and interestingly enough remains constant. Okay, this is the kind of problem where it surely wouldn't remain constant as we were burning fuel, but we're going to pretend that we didn't burn much fuel and that it does remain constant. So mass is constant. Our starting velocity for the lunar lander is a positive 6, where down is positive. And then we will have our summation of impulse integrals, and we're going to have 2 of them because we have an impulse due to gravity, but that's a constant. So integrating a constant over time is merely the value of the constant times the difference in time. Okay, so a 5-second time interval for gravity acting the entire time, and gravity acts down, positive is down, therefore it gets a positive sign. For the thrust of the rocket motor, it varies with time, which means we actually have to work out our impulse integral. And one way to integrate is just realize it is the area under the curve. So the entire impulse interval is the area under the triangle plus the area under the block plus the area under 0 for 1 second, which is 0. So the area of the triangle is going to be an 800 tall times 2 wide. 800 times 2 gives us the rectangle. Divide that by 2. That gives us the triangle. And thrust is in the upward direction, which is negative for our coordinate system. So we'll say minus the 800 by 2 rectangle multiplied by 1/2 for the triangle. And then under our curve we have a full 800 by 2 area under the curve. So we have a full 800 by 2 also acting negative in the negative direction. So we have our starting momentum. We have the impulse due to gravity, that was a constant force. We have our impulse due to the thrust of the motor, that's a time varying force that we integrated by using areas. Then over on the right hand side of the equation we have mass times the final velocity. There is only one unknown in this thing, and so our final velocity is 2.1 meters per second. And that would be our velocity, presuming we have not actually hit the ground, and that's a fairly dangerous velocity for a lunar lander, moving 2 meters in 1 second. Okay, next problem. let's zoom in, look at the picture, look at our impulse curve, and look at the words. Okay, what we have is a motor and a log sitting on the ground. This motor is going to put out a certain force as a function of time by spinning the motor. This is the force versus time curve, in which the motor has to ramp up its force over a 4-second interval until it reaches a 6,400, is that pounds? No, that's 6,400 Newton maximum force. And then after the 4 seconds, the motor is able to put out a constant 6,400 Newton force for presumably an unlimited amount of time, or they'll tell us how to limit it. Now what's interesting is, as the motor is ramping up in force, that the small forces early in the processes are unable to overcome static friction, so nothing moves. There will come a time, and we'll have to calculate where that is, when the motor force is just the same size as mu static times n. At that point, the log breaks free and begins to move. And then, so we need to know where that is, because the impulse that we'll be dealing with will only be of interest once the log is moving, and I'll explain why. Let me go ahead and do that now. While my motor force is too low to move the log, looking at a free body of the log says I've got motor force, I've got gravity acting downward, I've got normal acting upward, and I've got friction in fighting the motor force. Now, if I'm not moving, what is the size of the friction? And remember, when I'm not moving, the friction force is less than or equal to mu static times the normal force. It's not equal to mu static times n, it's less than or equal. But when my force is not able to move the log, then my friction force precisely cancels the rope force. Only when my rope force gets bigger than mu times n, because as my rope force grows, it slowly brings the friction force up to precisely mu static times n. At that point, the log breaks free, starts to move, and after that, the dynamic version of friction, kinematic friction force, will be precisely equal to mu times n. So we need to find the spot where it breaks free, and while it's not moving, this impulse cancels that impulse directly. Once it's moving, this impulse will be bigger than that one, and we'll be able to deal with that. So let's read the problem statement. It says the log has a mass of 500 kilograms and rests on the ground, for which the coefficient of static and kinetic frictions are mu equal 0.5 and mu equal 0.4 respectively. The winch delivers a towing force T to its cable at A, which varies as shown in the graph. How much time is required to give the log a speed of 15 meters per second? Originally, the cable tension is 0. Hint: first determine the force needed to begin moving the log. That'd be that break free point, at which rope tension equals mu static times n. And so we can first, and let me zoom out a bit, sum forces in the y direction is equal to mass times acceleration in the y, which is equal to 0 because we're not moving in the y direction. And notice our coordinate system, y and x. So the normal force acts in the positive y, gravity acts in the negative y, so n minus mg equals 0, which means the normal force is precisely equal to mg, mass of 500, g of 9.8, and therefore 4905 newtons of weight for the log. Alright, now we're going to look at the static part of the problem where the log has not moved yet, and we're going to want to find the force in the rope that will precisely equal mu static times n. So, summing forces in the x direction will have a positive rope force and a negative friction force. Positive rope force called T sub I, and that's the force that will cause the thing to break free, minus the friction force, mu static times N, is equal to 0 because we have not quite started moving. We're fixing to move at this point in the problem. And so we know mu static, we've already solved for N in the previous part, and so our initial tension is going to be 0.5 mu S times N of 4905, or 2452.5 newtons is the tension we have to have in the rope before we can begin moving. Now notice we have an equation for rope tension as a function of time. Rope tension is 400 times time squared, and so we can solve then for the time to reach the tension to break free. So our tension is 2452 at the break free point, is equal to 400 times the time at the break free point, one equation, one unknown, and we can solve for the time at the point when the log breaks free for the first time of 2.476 seconds. Alright, we haven't done much in the problem yet, but we do know when the log begins to move. Now we want to use the full momentum equation, impulse momentum equation, to figure out how long it takes for the log to move 15 meters? No, achieve a velocity or a speed of 15 meters per second. We will need to keep in mind that time that we were standing around waiting as part of the total time. So, our general impulse momentum equation applied to the log says our starting momentum, but we started from rest, so that V equals 0, so our starting momentum is 0. Then we're going to have impulses that come from the motor, and we'll have impulses that come from friction. The motor impulse is not constant. Sorry, the motor force is not constant, but the friction force is constant. And so starting momentum, sum of all impulses, is equal to final momentum. Some of the impulses would be positive, tending to increase the momentum. Some of the impulses, particularly the friction, would be negative, trying to reduce the momentum. So our starting momentum term is 0. We have a period where the motor is ramping up following the 400 T squared force formula, and this occurs between our starting time where we broke free, T1, and this particular profile ends at 4 seconds. Now, we're going to make a wild guess, or an educated guess, that it takes more than 4 seconds total for the log to reach its peak, the speed of 15 meters per second. So after our curve ramps up for 4 seconds, then our curve reaches a constant force of 6,400, but that will be true only after T crosses 4, and so we'll put a T minus 4 in there, and so these two terms are the positive motor impulse terms. Then we have friction acting as a constant the entire time. The friction is mu k times n, and we know both of those numbers. And the friction kinetic operates only over the time interval break free time and the time it takes to reach 15 meters per second. So this is our friction impulse, the area under the constant friction curve. And then finally, on the right-hand side of the equation, we have the final momentum, mass times the velocity of the log at time 2. Plugging in everything, so integrating the T squared term, we get a T cubed over 3 from T initial, which we got on the previous page, to 4. This thing goes from 4 to T. This one goes from T initial to T, and we have our mass times our final velocity. That final velocity is known. If you look carefully, this is a one equation, one unknown problem in T, and we can solve for a value of T is 4.9 seconds. And so we just barely got into the flat spot of the motor tension curve, because at time equal 4, we're here. At time equal 4.9 seconds, we reached 15 meters per second of speed. This is a bit of an accounting problem. We had to account for the starting momentum. We had to account for the area under and this integral is the area under the parabolic part of this curve. It's the area under that goes from the starting point all the way out to 4 seconds, is that area. Then finally we had the area under the flat spot. So area under the quadratic piece is a cubic, area under the flat spot, the area under the friction versus time curve, but friction is a constant. Then finally our final momentum gives us our final answer. It's a bit of an accounting problem. Okay, next let's read the problem statement, zoom in quite a bit, and then look at the picture. It's about as far as I can zoom. Let's bring that there and let that settle down for just a second. It says a block has a mass of 5 kilograms and it's released from rest at a point A. It slides down the smooth plane onto the rough surface having a coefficient of kinetic friction mu k is equal to 0.2. Determine the total time of travel before the block stops sliding. Also, how far does the block slide before stopping? Neglect the size of the block. So time is involved, 2 different velocities at various locations are involved, and with time and velocities involved, that's a momentum problem. But then at the end they threw in the little kicker and they said how far does it slide. That could be an energy problem. All of these could be chapter 13 problems. And so let's see what we've got. Let's look at the picture. First of all, we're told in the picture the block slides down this smooth frictionless surface, and we know the angle and we know the height to point A. So we know a lot of distance stuff in this first part, and we don't really know anything about time in the first part. So we're probably going to work an energy problem since we understand only distance stuff. And maybe once we work the energy problem, we can figure out the time stuff. Then we transition to a rough surface where friction kicks in. And we want to know about time stuff and we want to know about distance stuff. Let's start the problem off. Let me zoom out. This might be a touch far. And for the first part of the slide, since we know mostly distance stuff, we're going to start with energy. Okay, T1 plus V1 equal T2 plus V2. Where did the non-conservative work go? There is none because there's no friction or human effort. So we're starting from rest, so T1 is 0. We're starting from up high, so let's say that we have some MGH. And that's all we have. There's no spring, so we have kinetic energy of 0 and gravitational potential. Then on the other side of the equal sign, we have our kinetic energy at the corner point when we transition between the 2 paths. And we have our gravitational potential, which has gone to 0 because we use the low spot as the reference. And there's no spring, so there's nothing else to add. And this is a pure MGH turns into 1/2 mv squared kind of problem. And so our final velocity is the only unknown in this equation, because we know m and we know g and we know h and we know m. So our final velocity is the square root of 2gh. We're going to see this equation a fair amount. That final velocity starting from rest when we fall through gravity is the square root of 2gh. And because of the height we started at 3 meters, using a g of 9.81, then we have a final velocity of 7.67 meters per second. That's how fast we're traveling when we reach that corner point. Okay? Now that we know velocity at the beginning, velocity at the end, and we understand the forces that are acting, we can now choose to turn this into a time-based problem, making it an impulse momentum problem. Because now we're a little bit smarter now since we know both velocities. So let's do that. And we're going to find out the time to travel down the incline using starting momentum plus the sum of all linear impulses is equal to the final linear momentum. We started from rest, so our starting linear momentum is 0. What forces are acting on this thing as we head down the hill? Our free body diagram as we head down the hill says we have a normal force and we have gravity, and there's an angle between the two because it's on a straight line constant slope. And so what we will do is talk about momentum in the downhill direction. So we ought to label the coordinate system, and let's call that our positive direction for our momentum equation. And so what we're going to have, starting mass times starting velocity, but that starting velocity is 0. The only force that is not canceled, let's talk about that a minute. This gravity piece can be turned into a gravity piece that cancels, that is exactly equal to the normal force, and a gravity piece that is moving us downhill. This impulse precisely cancels that impulse. These two forces at all times are equal and opposite. They cancel. Only the piece of gravity aligned downhill, or the component of gravity aligned downhill, will cause an impulse in the downhill direction. And so that's going to be an mg with the opposite side, an mg sine of theta piece, acting in the positive downhill direction. So 0 starting momentum. The force is mg sine of theta, a constant. Therefore, the impulse is the area under the constant curve, so we just multiply by the time required, is equal to our final mass times velocity. We know that that's 0. We know the final velocity from the energy problem that we solved back here. So we know that final velocity. The only thing we don't know in this equation is the time required to get down the slope. And so we will algebraically solve for the time and come up with 1.5 seconds to travel down the straight line slope. Okay? Now the question is, how much time does it take to travel along the flat part of the path, given that we now have friction and have to deal with that impulse? So we'll work that time problem, because we know the velocity here, we know the velocity here, we know the velocity both places, we know the forces, so we ought to be able to, and the forces are constant, so we ought to be able to work out the time from the momentum equation. Starting momentum at the corner point plus the sum of all impulses adding momentum to the system is equal to the final momentum of the system. In this case, we come to rest, so the final momentum of the system is 0. Our starting momentum is the mass of the block times the velocity at the corner point, which we've already known for a while. And the only impulses acting in the horizontal direction would come from the forces acting in the horizontal direction, and we're going to call traveling to the right positive. That way velocities to the right would be positive, so we're going to mark that as a plus. We have gravity always being canceled by the normal force. Whatever impulse that has is precisely canceled by that impulse. We will ignore it. All that's left is the impulse due to friction. Friction is a constant mu n because it's moving, and since friction is a constant, the area under the constant friction curve is simply the friction force times time. And the friction force is in the negative direction, so it's going to be a negative impulse. So we have starting momentum minus the force, mu k times n, integrating under the force curve for a duration t2. This is the amount of time that it slides on the second part of the problem. Finally is equal to 0. We do know this velocity. This is the velocity at the corner. We've known it for a while. We know mu and n. The only unknown is t2. Flipping the page and plugging in the numbers, solving for t2 gives us 3.91 seconds of sliding time on the horizontal part of the path. But that's only the horizontal part. The total sliding time is 1.56 down the hill plus 3.91 on the flat spot, for a total travel time of 5.47 seconds before it comes to a stop. Now that we know for the flat spot the starting velocity, the final velocity, we could call that V1 and V2. We know those velocities. We have just found the time that will take us from here to there, and we are looking for the delta S, the distance we slide from here to there. And so there are several ways that we could solve this. Knowing our two velocities and the friction force doing work, you could write an energy equation to solve this. I don't actually have that in my notes, so let's go ahead and write an energy equation that says at the start of the path I've got energy 1/2 mv squared. At the end of the path I've got velocity equals 0, so no energy there, and I've got a work term from friction, so there will be a non-conservative term there. So I will have 1/2 mv1 squared, and then in the process of traveling from high speed here to stop there, does friction add energy or does friction remove energy? Friction removes energy from me. It slows me down. So I'm going to have minus a work term, and it's a constant force acting through a distance, and that force is mu k times n, which I know. That's the force. The work done by that force is the distance d, or delta s. Maybe I should have called it delta s. And then on the other side we have the starting energy, non-conservative work, force dot distance is equal to final kinetic energy. At this point I know my velocity at the kink point, I know mu and n. That distance is the only unknown. I'm not going to solve for it here, because when I solve for it down here I'm going to get almost 15 meters, and when I solve it a different way I'm going to get almost 15 meters. So if you would like to check and make sure that 15 meters works right here, but it will. Another way to solve for that distance is to notice we've got delta v's and a delta t, and we have constant force, therefore we have constant acceleration, and so we could use the constant acceleration formulas that involve finding the delta s, knowing the delta v's and the t's, but knowing the acceleration. What's the acceleration? We can get that by summing forces in the x direction, setting that equal to mass times acceleration. The only force acting in the x direction is friction, and it's acting in the negative x direction. So mu times the normal force, mg, mu times the weight, is equal to mass times acceleration. Mass cancels, and so our acceleration that comes from the friction force is equal to minus 0.2 times 9.81, or the acceleration, which is really a deceleration since it's negative. The deceleration in the x direction is 1.962 meters per second squared. Knowing A, knowing starting velocity, knowing the time of travel, we've already solved for that, knowing I'm going to start at a position of 0 and wondering how far I'm going to slide, and I also know that time term because I know time everywhere. I plug in everything known on the right hand side with my position equation for constant acceleration and come up with 14.99 meters. The other side of this page says, you know what, we could have used the ADS equal VDV term, okay, and integrates it, but we didn't have to integrate it. We could have gone straight to the V final squared is equal to V initial squared plus 2AX delta S. We could have gone to that equation, and we know V initial, we know V final is 0, and we just solve for the acceleration. We could solve directly for delta S, either using time or using the ADS equal VDV, or we could have used energy, or we could have done an integral of ADS equal VDV if we wanted to. A lot of different ways we can get that distance. The best way is probably with energy. It is one equation, one unknown, didn't have to bother solving for acceleration. Okay, the next section of problems will deal with the conservation, highlighting that word, conservation of linear momentum. Alright, what that means is, if momentum is conserved, our starting momentum is our final momentum. If there are no impulses during the time when I transition from beginning to end, if there are no unmatched or unbalanced impulses. Okay, Let's talk about this though for a particle of, or for a system of particles, multiple particles. So we are going to put summations on these things. Now, one way we may view multiple particles is as a collection of particles that right now together have a center of gravity, and that vector center of gravity has a vector average velocity for the center of particles. So we could represent this as the mass times the average velocity of the particles at the center of gravity, but that's what comes from the sum of all the individual masses times the individual velocities of all the particles. Okay, and this mass term right here is simply the sum of all the individual masses. Okay, if that's true, we can say that the momentum of the group of particles referenced by its center of gravity velocity to start the problem is equal to the momentum mass of the total set of particles times the velocity of the center of gravity of particles at state 2. But if the masses don't change, if we don't add or remove mass, then we can cancel the mass. And what this says is if we have lots of particles, the velocity of the center of gravity of the particles in position 1 is equal to the velocity of the center of gravity of all the particles in position 2. The velocity of the center of gravity does not change in a conservation of momentum problem. And then there's another interesting situation. Okay, what if the initial velocity of the center of gravity of the particles is 0? Then that must mean it remains to be 0 here. Okay, and if the velocity of the center of gravity starts at 0 and ends at 0, that also says that the center of mass did not move if it had 0 velocity the entire time. So the center of mass of the system is at a constant location or doesn't change. And we can take advantage of that in some problems. Okay. This is a busy little problem because we're asking for a few things and we're asking for some different things. Let's zoom in, get this right. Okay, what we have is a block on a slant. The block will slide down the slant from a given height, turn the corner, and right before it jumps onto this cart, it will have achieved a certain speed because height turns into speed. Okay, then we want to know what happens after it leaves the spot and then interacts with the cart. And we're going to allow in this problem two things to happen. In one case, we're going to allow the block to slide onto the cart, and initially the cart's stationary and the block has a known velocity. But eventually, the friction between the block and the cart causes the cart to speed up. The friction between the cart and the block causes the block to slow down until they come to the same velocity, and all of a sudden the cart and the block are rolling along happily as one object. That'd be one scenario. The other scenario is let's tie the cart to this frame and let's let the cart simply act as another landing area. And then an interesting question would be, how far does the block slide onto the cart, maybe before it comes to a stop or reaches a certain speed. But this is the geometry. Let's look at the details of the problem statement. Again, I'm zoomed in about as much as I can. We'll let that focus for a second. A 40-pound box slides from rest down the smooth, frictionless, I added the word frictionless, ramp onto the surface of a 20-pound cart. Determine the speed of the box at the instant it stops sliding on the cart. That means both the cart and the box are moving together then. If someone ties the cart to the ramp at B, determine the horizontal impulse the box will exert at C in order to stop its motion. Neglect friction and the size of the box. And actually this problem statement has a little bit of a problem. We can't neglect friction between the cart and the box, otherwise they won't come to a stop. What we're being told is don't worry about the value of the friction between the cart and the box, because you won't need it to answer the precise question asked, which was determine the horizontal impulse the box will exert onto the cart, okay, to come to a stop. But we weren't asked for the distance and we weren't asked for time. So let's see how this all hangs together. The first part is a simple energy problem to get the cart from up high, if you get the box from up high, down to where it's fixing to jump on the cart. That's an energy problem, and it's going to be, let's exchange height for velocity. And it did start from rest. Let me zoom out so I don't mess up pointing to things. Let's see, that's probably reasonable. So our energy problem going from high to low is our starting kinetic plus starting potential is equal to final kinetic plus final potential. There are no springs, there's no friction, there's no human involved, so it is a conservation of energy problem. We're starting from rest, so our initial kinetic energy is 0. Our initial potential energy comes from gravity. It is a 40-pound box, so mg is 40 and h is 15. If we measure h from the bottom of the problem, and we're 15 feet above the bottom of the problem, so h is 15 feet. That takes care of everything on the left-hand side, so all we have is a gravitational potential energy term. On the right-hand side, we'll have a kinetic energy term. Gravitational potential energy will be 0, spring energy will be 0, so this is another just total exchange of gravitational potential, turns into 1/2 mv squared. The only unknown in this equation is b, the velocity of the box at the bottom of the ramp, and that comes out to be 31.08 feet per second. Now we know how to proceed on we have what we need to proceed on the other two parts of the problem. Okay, this part of the problem, let me remember, there is no rope. So what we're going to have for the cart and box system, two different bodies, when the cart, and at two different points in time. The first point in time is the box is just fixing to jump onto the cart. The final point in time will be when the cart and the box are traveling down the road together and the cart has stopped sliding, or the box has stopped sliding on the cart. So this is a conservation of momentum problem. There are no external impulses. Now we do have some internal impulses. The box imposes a friction force on the cart. That would be an impulse. But the cart imposes an equal and opposite friction force on the box. Those two friction impulses cancel each other. Therefore, we don't bring them into the problem, and so we don't have any impulses to deal with that don't cancel each other. There are two that cancel each other. So we have our starting momentum of the cart, which is 0. The starting momentum of the box right before it jumps onto the cart is the mass of the box, W over G, times the velocity of the box, 31.08, that we saw for a moment ago. This takes into account the momentum of everything right before the box jumps onto the cart. After the box jumps onto the cart, and they have come to an equilibrium where sliding has stopped, that means both the cart and, you can't see this, sorry, I've been pointing to the cart. So, on the second side of this problem will be when the box is on the cart, let's draw it over here, and all sliding has stopped. Okay? And so what that means is both the cart and the box have achieved the same velocity. That's what no sliding means. So what we'll do is we'll say the mass of the box times the velocity they share plus the mass of the cart multiplied by the velocity they share. But we recognize they share the same velocity. We can just add the two masses together and treat it as one mass. And so the 40 plus 20 over the 32.2. So this one says cart is stationary, box is moving. Cart and box move at the same speed. The only unknown in this problem is the cart and box pair. Their speed of 20.7 feet per second is what happens as they are moving along, and the only thing that would cause this to slow down would be eventual friction or air drag that would bring it to a stop. Then the second question says somebody has tied the cart to the ramp. And so we want to understand what happens between the two times when the box is fixing to jump on the cart is one time. The cart never moves, but the box stops sliding on the cart. So at time 1, box has velocity. At time 2, box does not. The cart never has velocity. And so in this problem, we have our starting momentum. We do have, from the point of view of the box, an uncountered impulse, and then a final momentum of the box. The final momentum of the box is 0. It comes to a stop. The starting momentum of the box is mass times that 31.08 that we've used before. That's the corner velocity. And then the impulse will steal from this momentum and drive the velocity to 0. And so this impulse is going to be an integral of a force acting over time. Now, this impulse quantity right here, we can call I. And what were we asked for in the problem? Were we asked for time? Were we asked for distance? No, we were asked for I. So basically, this constant minus the I that we don't know equals 0. Solve for I. In this problem, since we don't know friction, we can't solve for the friction force. And if we can't solve for the friction force, we can't solve for the time. So we can't find those individual numbers, but we can find the area under the force-time curve using our impulse momentum equation. That ends that problem. Okay, another problem that involves conservation of momentum and a system that might have a center of gravity. So what we have is someone is walking on this cart. They will walk a distance of 6 feet, and they're going to start over here on the left hand side, and they're going to arrive at the right hand side and either and maybe just jump off, or we'll look at what happens right before they jump off. Okay, and if they start here and they start walking to the right, then their feet are going to be pushing this cart back to the left. Okay, and the question, it will be something like, how fast is the cart moving? How fast is the person moving? During this 6-foot travel walking distance, how far does the cart move? Interesting kind of questions like that could come up. Let's see what comes up. Let me zoom in until I can't zoom any further. Let's let that settle down. A 100-pound boy walks forward over the surface of the 60-pound cart with a constant speed of 3 feet per second relative to the cart. Boy, highlight that word, relative to the cart. We've encountered this idea before, and it made problems tougher. We had to write our equations a little different. So highlight that word, 3 feet per second relative to the cart. Determine the cart's speed and its displacement, or the distance it moved, at the moment that the boy is about to step off the cart. Neglect the mass of the wheels and assume that the cart and the boy are originally at rest. And so our solution process is, anytime we see this kind of interaction between people and carts, people and boats, those kinds of things, boats and boats, trains on boats, things like that, we're going to do a conservation of momentum. Now, why conservation of momentum? Doesn't the boy's feet cause the cart to gain velocity? Absolutely. Why? Because the force in his feet causes the cart to move to the left. But doesn't the force between the cart and the boy, that friction force, cause the boy to move to the right? The friction force between boy and cart equals the friction force between cart and boy. If we were to separate them into two pieces, there's a friction force that moves the boy forward. There's a friction force that moves the cart to the left. You can't see that. Here's the cart, here's the boy, drawn very badly. There's a friction force between the cart and the boy that moves the boy to the right. There's a friction force between the boy and the cart that moves the cart to the left. At every instant, these two friction forces are equal. Therefore, the area under the force curve for each of these are equal and opposite. One's positive, one's negative. So these will be forces that cancel, therefore the impulses cancel, and there are no other uncanceled impulses for us to worry about, because gravity always cancels normal force in these kind of problems. So we will turn to our equation. Let's zoom out so that I don't get in trouble with the zooming. Give me a second. And we're going to say that starting momentum of the system is equal to the final momentum of the system. But the starting momentum and the summation here means sum over two things. The boy is one of the things, and the cart is one of the other thing. But in both cases, to start the problem, the boy has zero velocity and the cart has zero velocity. So the total momentum of the system at the beginning of the problem is zero. What does that mean from conservation of momentum? It means the total momentum of the system at the end of the problem must be zero. Now remember, momentum is a vector. It has direction. It has sign. So on the right hand side, this is the momentum of the boy at the end of the problem. This is the momentum of the cart at the end of the problem. But these two must add to zero. The masses are positive, so for them to add to zero, one of these velocities has to be positive and one of them has to be negative. We will define to the right as positive, so in the end we'll expect the boy's velocity to be a positive number. We'll expect the cart velocity to be a negative number. Key thing to notice at this point in time, one equation, how many unknowns? We know the masses of everything, but we don't know the velocity of the boy or the velocity of the cart. Velocity of boy, velocity of cart. We don't know either of those right now, and so we've got one equation, two unknowns. So we need another equation. That's where we highlight that word relative one more time. The boy has a constant speed, 3 feet per second, relative to the cart. So we write a relative velocity equation that says the true velocity of the boy is the true velocity of the cart. That's these two variables. Plus the velocity of the boy with respect to the cart. I check my orientation here. C in the numerator cancels C in the denominator, leaving a B in the numerator, which matches a B in the numerator on the other side. And we will write this velocity of cart plus the relative velocity of the boy with respect to cart. We'll still leave this velocity of the cart here, but the relative velocity is a positive 3. So we have the velocity of the boy equals that. So let's just put velocity of the boy there. This is another equation. It's our equation number 2. And the unknowns in this equation are the velocity of the cart and the velocity of the boy, neither of which are showing up for the first time. Therefore, we have a two equation, two unknown set. And from these two equations and two unknowns, we can solve for both the velocity of the cart and the velocity of the boy at the end of the process. And so solving those two equations, two unknowns, gives us the velocity of the cart at the end of the process is minus 1.875 feet per second. And the velocity of the boy at the end of the process would be 3 plus this negative number, or somewhere in the neighborhood of about a 1.2 positive. We didn't actually calculate that. Okay, now the question is, how far did the cart move? We know that the cart has acquired a constant minus 1.875 feet per second velocity, and if we knew how long it had that velocity, then we could figure out the distance it moved, because it's a constant velocity. Well, another way of answering the same question is to say, how long did it take the boy to walk all the way across the cart when the distance he had to walk was 6 feet, and he was walking at a relative speed on the cart of 3 feet per second? And so, formalizing that problem, the distance traveled of the boy on the cart is the velocity of the boy relative to the cart times time. The distance he traveled relative to the cart was 6. The speed he traveled relative to the cart was 3, which means it took him 2 seconds to walk across that 6-foot cart at a relative speed of 3 feet per second. Now that we know that the entire event took 2 seconds, we can go back and look at the cart, which requires this constant velocity, and this constant velocity times time will give us the distance it traveled. The distance the cart travels is the velocity of the cart times time. Here's its velocity, a time of 2 seconds, or the cart travels a negative 3.7 feet to the left. Should be the end of that problem. It is. The final problem we encounter is just an absolute classic. Let me zoom in on the picture. Let's look at the picture. What we have is a box, probably full of sand. We'll see when we read the problem statement. We have fired a bullet at that box of sand. That bullet will impact this box and cause the box to begin to swing on this rope. Now we will be ignoring any angle change of the box and any energy required to change the angle of the box. We'll be ignoring that and really just paying attention to how high the box goes. And so what we would hope to learn from this maybe is if we can measure how high the box goes, we might be able to work a big old pair of math problems and figure out how fast the bullet was going. So this problem is likely to be either if the bullet's moving at a certain speed, how high does the box swing? If the box swings, or if the box swings a certain height, how fast was the bullet going? But this is a two-stage, actually this is a potentially a three-stage process depending on how the bullet arrives. There is the bullet is way back here, and then to the point where the bullet is just fixing to hit the box. That doesn't really need 2 stages. So our first stage will be bullet is just fixing to hit the box. Then the next stage is bullet travels into the box and embeds itself into the box somewhere. Now, what does it mean for the bullet to embed itself into the box? It means the bullet stops moving relative to the box, okay? Or the bullet and the box are moving at exactly the same speed. That process where the bullet buries itself into the box and achieves the same speed as the box, we're going to call an impact process. That takes some time. So our stage 1 is pre-collision. Our stage 2 is right after the impact process is over, but the box is barely, I mean just barely started to swing up, and we will actually ignore the amount that the box has swung up while the impact process is happening. We're going to assume the impact process takes an unknowable, very small amount of time. Then, so that will be the other stage, bullet buried in box, but the box isn't, and the box hasn't traveled any distance yet. Then the final stage will be box reaches the top of its swing, really horizontal, not rotated. Okay, and we can say something about how high the box has gone based on the velocity that it acquired here, because as the bullet buries itself inside the box will acquire some velocity. That's the physics of the problem. Let's look at the words of the problem. So it says a ballistic pendulum is a simple device to determining ballistic velocities. The 60-gram bullet is fired into the 30-kilogram box of sand suspended by a simple pendulum. If the pendulum is observed to swing through a maximum angle of theta equals 15 degrees, after the impact, compute the muzzle velocity of the bullet and the percentage loss of energy of the system during the impact with the sand. And they gave us a couple of answer numbers. So, knowing how high we went, predict the speed of the bullet, and this entire system, there will be energy loss as the bullet travels into the sand. There will be friction there. That friction will cause heat. That'll be an energy loss, and we want to calculate the amount of energy loss. So on this problem, let's go ahead and talk about states. There is a state 0, which is fixing to hit. Okay. There's a state 1, in which the box and the bullets are fixing to move. They've just acquired some velocity, the box has, and they're fixing to move, but they haven't moved yet. They haven't acquired any height. Then there's a state 2 where box swings to stop. Okay. What do we know at the various states? We know that V of the bullet is equal to unknown, and as a matter of fact we want it, and we know that V of the box equals 0. Then as the bullet has hit the box and has buried itself into the box and caused the box to start moving, this process we will call impact. But we will also make the argument that this process is conservation of momentum. Okay, we'll also make the argument that this process is not, absolutely not conservation of energy. It's conservation of momentum. Then as the box has acquired some velocity with the bullet inside of it, but it hasn't moved yet, we will allow the box to move and swing up to a certain height and come to V box equals 0. Okay, and that's going to be an energy problem. And in the middle we have V bullet is unknown, and we have V box is equal to unknown. But what we do know is at this point the bullet has come to a stop inside the box. The bullet and the box are traveling at the same speed, and so we do know that V of the bullet equals V of the box. We know that. Alright. Okay, we have impact between bullet and box. Bullet travels and slides through the sand, and there's all kind of friction going on. Clearly not conservation of energy, because there's a lot of friction throwing energy away. But how can we say conservation of momentum during this interesting kind of impact? Because if we have the box and the bullet is traveling inside of it, the sand will impose a friction force on the bullet to slow the bullet down inside the box, and that friction force will exist until the bullet and the box reach the same speed. If the box remained at 0 speed, then the bullet would come to 0 speed. But there's actually something letting the box acquire velocity, because the bullet also imposes a friction force on the box. What's the size of these two friction forces? Always equal and opposite. Okay? If the forces always cancel, then what's the impulse? Each of these impulses will cancel. We also have the rope force, actually rope force acting upward, and we have gravity force acting downward, but they're always, during this process, equal and opposite. These forces cancel, therefore their impulses cancel. There are no unmatched forces, therefore there are no external or unmatched impulses. So if there are no impulses, then we have conservation of momentum. Okay, we're going to talk about 3 kinds of impact in this chapter. This one I call the hit and stick. The bullet hits the box and it sticks to the box, meaning they acquire the same velocity. Alright, let's put the math together on this problem. Again, let me zoom out so I don't lose you. Probably a decent size. Okay. Because we know the most here, because we also know that theta is equal to, what'd they say, 15 degrees? Okay. We know the most stuff here because we know the velocity of the bullet and the box together is 0, and we know how high it went. We can use energy to work our way back to this part of the problem and learn the velocity of the bullet and the box combo here, because 0 speed but height turns into speed. Now, looking at a swing problem, you might remember from an earlier swing problem, the girl on a swing, a 1 minus cosine jumped into the problem. That almost always happen when we measure the internal of the angle of the swing. Let's look at the problem again of how high the swing goes. Box starts here, box ends up here. We have a quantity called h, which is the height change. Let's see. Let's measure it from the top of the box. We have a height change h when it swings up. We have a rope length r. That's the entire rope length. I didn't draw my picture beautifully because it looks like the rope got shorter, but the rope did not get shorter. So I also have a rope length r here. And if I were to know the angle here, theta, which I do, then r is this entire length. But this distance right here is the distance from the center point to that line right there is r cosine of the interior angle theta. Okay? And this entire distance is r, which means this entire distance is r. So, how much is h? H is equal to r, the total height, minus this height, r cosine of theta. R minus r cosine of theta, which also can be written as r times 1 minus the cosine of theta, is the height. H equals r times 1 minus cosine of theta. That shows up an awful lot in swing problems when the interior angle is measured. Not true when the exterior angle is measured. And so, our energy equation is going to involve the height. So let's just calculate the height all by itself. It is r times 1 minus cosine of theta. R is 3, theta is 15 degrees. So the height through which we swing from the bottom of the problem to the highest point is 0.1022 meters. Okay? Now, our energy problem says, I don't like the way this is written. It says we're going to have a T1 plus V1 equal T2 plus V2. It's a conservation of energy. And our 1 point will be up high, and our 2 point will be down low. And up high we have no velocity, but we got some MGH. When we reach the bottom of the problem, we'll have some speed, but we won't have any MGH. So MGH turns into 1/2 mv squared. So 1/2 mv squared minus the MGH equals 0. Solving for v is the square root of 2gh. We've seen that before. And h is that r times 1 minus cosine term. Okay, for h times 2g gives us a velocity of the box and bullet at the bottom of the swing. Now, let's see. And mass canceled out of the problem. We did not need mass to solve this part of it. Okay? Because mass canceled. Now, what about, so we've traveled from here to here, from here to here, and learned that the velocity of the box was 1.416 meters per second. That's also the velocity of the bullet. We've learned the middle part. Now let's work backwards from here to there using impact, which is, for this problem, is conservation of momentum. And so during the impact, Momentum is conserved. So our starting momentum, which is everything moving before impact, is equal to final momentum, everything that's moving after impact. Before the impact, the only thing that's moving is the bullet. And its momentum is the mass of the bullet times the speed of the bullet. After the impact, but before the swing starts, the mass, the bullet has embedded itself in the box. They become one body, having a total mass of 30 plus 0.06. And that combined mass is traveling with the velocity we found from the energy problem of 1.416. The only unknown in this question is the speed of the bullet before impact, and we get a speed of 710 meters per second, and I believe that's way beyond supersonic. I think that's a pretty fast bullet, like maybe about 2100 feet per second or something like that. I think that's a fairly fast bullet. Now, the question is, did we lose any energy? We had to. As bullet is going through the box, friction occurs. That friction heats up the bullet. That friction heats up the box. That heat is energy, and we are losing energy as the box springs the bullet, not to a stop, because the bullet speeds the box up a little bit. They come to an equilibrium. So how can we calculate the energy lost during the process? What we can look at is the energy we start with, okay, and that would be the bullet energy, 1/2 mv squared for the bullet, and then we could either compare that to 1/2 mv squared for the pair afterwards, or we could compare it to mgh. Either one of those would be a fine comparison. So let's see what we do here. Okay, so comparing the kinetic energies before and after the impact, our change in kinetic energy divided by the kinetic energy before the impact will give us an indication of what fraction of energy we lost. T is the energy of everything before impact. T prime will be the energy of everything after impact, and this will be the energy of everything before impact. Well, this can be written as 1 minus T prime over T. Now, T prime is the energy of everything after the impact. That's 1/2 the mass of the bullet and the box combined times the velocity of the combined bullet box squared. The energy before impact is only the bullet, 1/2 the mass of the bullet times the velocity of the bullet squared. If we've lost energy, we would expect the numerator to be smaller than the denominator. It is by a fairly small amount, because 1 minus the percent energy lost is 0.998. We have retained 99.8% of the energy, which means we have lost 0.2% of the energy. And so, even though momentum was conserved during the process, we have in fact lost some energy. What fraction of the energy did we lose? That term right there, which is approximately 0.2%. So energy was not conserved during the impact. Okay, and here's the big deal. Anytime you see an impact and you don't know what to do, do not automatically assume conservation of energy. That would almost certainly be false and a big mistake. Now, this finishes Chapter 15 for the next homework set that you'll be responsible for Monday. It also finishes the material for test number 2. The material for test number 2 will be the last piece of Chapter 13, F equal ma in cylindrical coordinates. All of Chapter 14, work and energy, conservation of energy, and power. And the first part of Chapter 15, which is impulse momentum, conservation of momentum, and impacts that involve hit and stick only, which are a conservation of momentum kind of problem. And so we'll look at do some test reviews, over the next few days. Tomorrow in class we'll look at some more of these kind of problems. But this finishes my notes for this section of the course.